Imagine sitting for the bar exam. You've spent years in law school, buried under mountains of case law, statutes, and grueling practice tests. It sounds like the pinnacle of machine cognition, doesn't it? Yet, if you were to ask that same brilliant software to explain why a glass of water tips over when you push it off a table, it might struggle to grasp the physical reality of the situation. We have built systems that can mimic the output of a genius while occasionally stumbling over the logic of a toddler. Research shows that large language models, the complex mathematical engines that power modern chatbots, have become incredibly proficient at pattern recognition. They process vast oceans of text, identifying the statistical probability of which word should follow the next. But engineers have developed these tools using a process called training, which essentially forces the model to encode the structure of human communication into a massive numerical map. Because of this, data suggests that these systems aren't necessarily learning in the way you or I might acquire knowledge. Think of it like a student who memorizes every answer key in a textbook without ever understanding the underlying physics or history. They can ace the test, but if you change the wording of a question just enough to require genuine insight, the entire house of cards collapses. This phenomenon is often called stochastic parroting, where the machine acts as a sophisticated mirror, reflecting our own collective knowledge back at us without ever truly comprehending the meaning behind the syllables. If an AI can write a legal brief but fails to understand that a physical object cannot exist in two places at once, can we honestly call it intelligent? Or are we simply witnessing an elaborate parlor trick played by billions of parameters? Let's move beyond the exam scores and examine the architecture itself to see if these machines are truly building mental models, or if they are just repeating what they have been fed. To understand the engine under the hood, we have to look back at the era of symbolic AI. Engineers spent years handcrafting vast libraries of if-then statements, trying to teach a machine how to interpret the world by brute force instruction. It was precise, predictable, and ultimately brittle. If you encountered a scenario the programmer hadn't explicitly anticipated, the system simply crashed or returned a null value. The pivot occurred when researchers realized that human knowledge is far too messy and nuanced to be trapped in a static rulebook. This shift toward neural networks fundamentally changed the game. Instead of hard-coding logic, we created layers of artificial neurons designed to adjust their own connections based on incoming information. But as research shows, the real breakthrough wasn't just the architecture. It was the arrival of the big data epoch. Data suggests that when you scale these models to a massive size, something emergent happens. The network stops merely memorizing specific examples and begins to identify complex underlying patterns, mathematical representations of structure, grammar, and even conceptual relationships. It is a process of constant refinement, where the model makes a prediction, compares it against the reality of the dataset, and adjusts its internal weights to minimize error. We moved from the era of the architect, who designed every brick, to the era of the gardener, who creates the conditions for patterns to grow. However, this reliance on statistical probability creates a massive blind spot. It doesn't experience the world. It processes the mathematical shadows that the world leaves behind on the internet. To determine if this pattern recognition is just a sophisticated game of connect the dots, we need to examine how these models handle the concept of reasoning itself, and whether they can apply their knowledge to problems they haven't encountered before. To unpack this mystery, we have to pull back the curtain on the engine room of the modern large language model, the transformer architecture. Instead, it translates your query into a high-dimensional mathematical space. Think of it as a vast, multi-layered map where every word, concept, and grammatical relationship is assigned a coordinate. It's essentially playing a game of statistical completion, where the objective is to minimize the mathematical distance between its output and the patterns it ingested during its training phase. When the model generates a paragraph, it is navigating a probabilistic web. If you provide the prompt, "The sky is," the model doesn't look up at the clouds. It consults its training data, identifies that the word blue appears with the highest frequency in similar contexts, and selects it. Data suggests that these models are essentially stochastic parrots, reflecting the biases, structures, and linguistic habits of the human internet back at us. They aren't reasoning through a problem, they are performing a sophisticated form of pattern matching that mimics the cadence of human thought. If you change the wording slightly, shifting the variables of a classic riddle, the model might fail entirely. It lacks an internal model of reality. It doesn't know that gravity exists. It just knows that, in the text it has processed, objects that are dropped tend to fall. True understanding requires a mental model, a way of simulating cause and effect independent of the specific words used to describe them. Without that, we are left with a system that is incredibly gifted at mimicking the appearance of intelligence while remaining entirely hollow at the center. However, just because this intelligence is synthetic and statistical doesn't mean it lacks utility. As we move forward, we have to consider whether this statistical mastery is merely a bridge to something more profound, or if we have hit a ceiling that no amount of extra data can break through. Regardless of the philosophical impasse, the practical impact of these engines is already rewriting the rulebook of modern labor. These systems aren't thinking about the patient's history or suffering. They are performing high-speed probability mapping against millions of documented cases to flag anomalies. In the realm of software development, developers are no longer just writing code line by line, they are curating logic flows generated by predictive models. Similarly, in creative production, we see a radical shift in how content is drafted, edited, and refined. Yet, this is where the most dangerous misunderstanding takes fruit. We treat the output as a product of intentionality, assuming that if the result looks like reasoning, there must be a mind behind the curtain. But this is a category error. When an AI offers a diagnosis or a piece of prose, it is simply navigating a multi-dimensional map of human language and data points, finding the most statistically likely path forward. It doesn't know what it is saying. It only knows what is most probable. We are building powerful, transformative tools that reshape our daily lives. Yet we risk losing our own intellectual agency if we confuse a calculator for a colleague. The machine is a mirror, not a consciousness. To recap, these systems are essentially massive statistical engines, optimized for pattern recognition rather than actual thought. They excel at scaling expertise across medicine, coding, and creative fields. Yet they remain tethered to the data they were fed, incapable of true innovation or independent judgment. We are standing at the threshold of a new technical epoch where the line between automation and intuition will continue to blur. If you found this exploration of technology fascinating, consider subscribing to keep pace with the evolving story of our digital world.